This video will begin our discussion of section 15.3. This is going to be adding on 15.2. So we're going to talk about how to find work of a particle moving through a path through a vector field, but we're going to focus on a certain type of vector field. We're going to work on conservative vector fields. Now, the thing is about conservative vector fields, we have a couple things. We have independence of path. This is talked about in 15.1. What that is if I'm in a conservative vector field, I do the same amount of work. Let's say I have this point here and this point here, and I'm going to take different paths between it. If it's a conservative vector field, the amount of work that's taken to get from here to here is the same thing as that. Or it's the same thing as straight to it. We could even go to the point that if I'm in a conservative vector field, I could do this and go back to the same point, and that would take zero work because that's the same thing as starting at a point and stopping at the same point. Conservative vector fields bring us independence of path, meaning it's the same amount of work from one point to another, regardless of which way you walk or your particle takes. Another definition for conservative was that if it was conservative, then I know that that path is some gradient for some function f. We don't know what function it is, but we do know that if it's conservative, there's guaranteed some function that when I take the gradient, I get back to the conservative vector field. Now, what's great about a conservative vector field? If it's independence of path, it does not matter which curve we take, which means this C here at the bottom, totally arbitrary. It could be whatever we wanted. It could be stand at one point, walk straight to the other. It could be walk 30 million circles and get to the other point before you get to it. We are going to use that idea. Curve doesn't matter. And then we're going to use this idea of the fundamental of calculus. The fundamental of calculus, if you remember that if I have a derivative, right, and I take the integral of the derivative, it is just the antiderivative f with each point subtracted through, right? It's just the antiderivative. Now, what's great about these gradients of f's is the way that we defined it was a function with multiple variables x, y, and z, but it was the partial derivative of each component. That is the derivative. So what that means is that if f is some gradient, I can't highlight, I guess, some gradient here, right? Then I know that the derivative of f is the gradient of f by definition. But since they are conservative, I know that I can find some f. So that means is if I was trying to find work, this means work, right? Really need you to get that in your head. This is work, right? If I need to find work, I could change that capital F to this gradient of f, and then I know that if I can find that f, then I can just use the fundamental theorem here and just plug in my endpoints, given that it's conservative. All right, I'm going to work a few examples. I like these. I feel like these last two sections just get easier the further we go. So the first thing we're going to do is show that something's conservative. I don't know if you remember that from 15.1, a couple sections ago. I know you guys are nearing the end here. That we can either show, given that our vector field is some vector p, I, and j, we can show that the partial of q with respect to x, that's the y component with respect to x, is equal to the p component, the x component with respect to y. Now, if there's an x, y, and z, what we have to do is show the curl is equal to 0. So we'll do a few of those in this section. Once we show that it's conservative, we are going to work backwards with this whole idea and set up a problem that's going to eventually look like that. All right, let's get an example in. All right, so I have find work on, okay, so this vector field, that is the vector field, and we're going to move from the point 0, 0 to negative 1, 1. So let's do that. The first thing we need to do is I label these because I'll mess it up, P and Q. And then I need to check that it's conservative. So the partial of Q with respect to X, it's the other one. Okay, so that ends up being a 2. Then I also take the partial P with respect to Y, and that gets me a 2. Since they are equal, then F is conservative. Since F is conservative, it's independence of path. I also, from that, get that F is equal to some gradient for some F. I know there's some function that when I take the gradient, I get F. So we're going to work backwards to get that. I know that F of xy, the way a vector field is defined, it is the partial of the partial of some f with respect to, and this is the way it's defined, that we have this, right? So that is some f partial with respect to xi plus the partial of f with partial of f with respect to yj. That is the gradient, right? That's how we take a gradient. That is the definition. So what we can do now is we can work backwards. I know that the partial of this f with respect to x is 2y plus 1. I grabbed that from up here because I know that's what that is, the way the big F is defined. Now, if I want to work backwards, though, I can find f of xy by taking the integral of that function, 2y plus 1, with respect to x. This would take me back, because that's how I know I got this, is I took that little f and took the partial with respect to x. So I'm going to work backwards to undo it. So if I do that, I get, we can introduce an x on both of those, 2xy plus x plus, now it's tempting to put c, but since it's a partial, we could have a function of y. Meaning if there was a y squared there, and I took the derivative with respect to x, it would just go to 0. So we have to add that in. So I have that f is equal to that. So if I have f and it's equal to that, I can take the partial of that f with respect to y. And it'll make sense why we're doing this in a moment. Okay, the derivative of 2xy with respect to y is 2x. Derivative of x with respect to y is gone. And then the derivative of hy with respect to y is h prime of y. Well, we actually have something else that is equal to the partial of f with respect to y. That is q. That's up here. So I can take this thing and set it equal to 2x plus 3. Well, I solved that equation. There's a 2x on both sides, so that gives me h prime of y equals 3. If I take the integral, right, antiderivative, I get 3y plus c. So I actually have this function, f of xy. It is 2xy plus x plus 3y plus c. That's the function. I don't know what c is, and it won't matter here. But the theory tells me once I can find this f, and you should check at this point, that f, if I take the gradient, I get big F. You should check that. Okay, so I have little f here. And the fundamental theory tells me if I want to find the work, which is the integral over the path c of big F dr, this is the same thing. I can replace the f with the gradient of little f dr, and this is equal to f of, and we take that first point, if we scroll up, the first a to b, we are going to do negative 1, 1, minus the lower point, which was 0, 0. So we plug both of these into our function that's above there. The 0, 0 just wipes them all out. The plus c's are going to go away with the minus. So all we have to do is plug negative 1 and 1 in, and we actually end up getting 0. So the work that was done here, let's actually plug that in. 2 times negative 1 times 1 plus negative 1 plus 3 times 1, that's going to work out to be 0. All right, that's just 0 work, right? We're walking from one point to the other point, could be downhill then uphill, something like that, where the forces cancel each other out. I like these problems. I think they are pretty straightforward, kind of gets us away from the vector stuff for a little bit too. This method is going to be very helpful when you guys go to diffEQ. If you're in diffEQ, this is like variation parameters, the way we solve those problems. Okay, example 2. So now we have that vector field, and we, on our xy plane, the particles moving from 0, 0 to negative 1, 1. So we could draw a picture if we wanted. Here's A, B is negative 1, 1, so it's here. So our particle is literally just moving from A to B on the xy plane. But this xy plane is put in that force field, the capital F. So we have all these forces moving us around. How much work would it take to stay on that path? Okay, so first we got to check to make sure it's conservative, because we can't use this method if not. If it's not conservative, you use the method from 15.2. All right, so I take the partial of q with respect to y, x, don't make that mistake, and we get 2x e to the 2y. Right? We also want to take the partial of p with respect to y. The 2 comes down, I get 2x e to y. Okay, so they're conservative, or it's conservative, f is. So f is conservative. That tells me that big F is equal to some little f, for some f, or some f. All right, so since that's true, I'm going to find that little f. So little f of xy is going to be, well, that tells me that this is, if it is conservative, that if I take the function I need, partial with x, I get that. And then this other one, I get the partial of f with the y. So I'm going to work backwards here, and I'm going to take that partial of f with respect to x, dx, to get me back. So that is the integral of x e to the 2y dx. I like these because usually the other function, like the y, doesn't play a part here, so I get to just do 1/2 x squared e to the 2y plus h of y. Because it's, if there was any functions of y, they're gone because that was the partial with respect to x. Right? I have f. Now I can try to work on trying to find that h of y. So I'm going to take f and take the derivative with respect to y. All right, we get x squared e to the 2y plus h prime of y. We set this equal to q, right? Q was x squared e to the 2y. That's nice. So h prime of y is equal to 0. This tells me, I know it's a bit weird, but if we integrate, hy equals c. So it's a 0, derivative of a constant is 0. So now I have f of xy. F of xy is 1/2 x squared e to the 2y, because hy was 0. Or c, I guess, we don't put c. All right, to find the work, I have work is equal to the integral of c f dr. I can replace that f with the gradient of f dr, which means now I can just do f of the points, I have it right here, was -1 to 1, same points, minus f of 0, 0. So plugging -1, 1 into that, we get 1/2 e squared minus 0. So we get 1/2 e to the second power. You can get decimal if you want. I prefer exact. Most people do. So, all right. So that is the amount of work to walk from point A to point B in that vector field. All those all the forces pushing around it would require that much work to counteract. All right. I just have more. A couple more examples. I think I have good 4 more. All right, the work done on that. So we have that from A to B. We could draw the points, but I think you understand. So we're going to start. First, we need to show that it's conservative. So the partial is q with respect to x. Okay, I get 2x. Oh, yeah, I did it right. 2x minus y over x squared. I think I'm doing, I wrote down the wrong one. I was looking at the wrong one. This is q. There we go. I was like, why is this different? We get 1 over x. Partial of p, that's the first one. This is why I label them. With respect to y, we get 1 over x. So, f is conservative, which tells me that some f, little f, is big F. So I can work backwards. Little f xy is the integral of partial of little f dx. Dx. Partial of f with respect to x dx. So this is equal to, okay, well that's p. So that's x squared plus y over x dx. All right, working this out, we get 1/3 x cubed. This is a bit tricky, but it's y ln of x. I know x is positive because it just goes 1 to e, so I don't need absolute value. Plus h prime of, just h of y. There could have been some y function that went away with our derivative. Now I take that same function and I take with respect to the derivative with respect to y. So we get ln of x plus h prime of y. And then we set this equal to q up at the top, which was y squared plus ln of x, h prime of y equals y squared. All right, so we have it set there. We're equal. Now we just got to find h of y. Take the antiderivative, so I get 1 over 3 y cubed plus c. So that tells me f now. F of xy is equal to 1/3 x cubed plus y ln of x plus 1/3 y cubed plus c. Right? So now I work through this. Work is over c over f dr. I can change the big F to the gradient of little f. And then this tells me I can use the fundamental theorem. So this is going to be little f of E1 minus f of 1, 0. You plug those into this function. And in the very end, you'll get 1/3 e to the third plus 1. Just check that out. Make sure you can plug in those points. Just algebra. The c's will go away. Okay, so that's the amount of work to go from A to B in that force field. All right, example 4, we're just going to find the work done on this, just set up the problem so we actually don't have bounds. All right, so the first thing is we have to show that it's conservative. So we have P and Q. So I have the partial of Q with respect to X. All right, that is going to be, okay, let me just show you another way to think about this. I could actually split that up. It's going to help us in a moment as well. I can do that. Partial with respect to x, I get 1 over 1 plus y squared. The partial with respect to q, partial of p with respect to y, if I could talk. All right, x goes away. The inverse tan becomes 1 over y squared. That tells me that f is conservative, which means I can find some delta f that will equal f. Or, sorry, it's del f, I guess, but the gradient of f. All right, so I work backwards. Little f of xy is equal to the integral of x plus arctan of y dx. All right, so I get 1/2 x squared plus x times tangent -1 arctan plus h of y. I know it's kind of weird, but the arctan of y didn't have an x, so we just could add one, thankfully. Now I take f and I take the partial derivative with respect to y. Right, the first term's gone. The second term we get x over 1 plus y squared plus h prime of y, and we're going to set this equal to q. So q is x over 1 plus y squared plus y over 1 plus y squared. That's what I did there. That's why we did it also, because that goes away. So we h prime of y equals y over 1 plus y squared. Right, this is a u sub. I'm going to let you figure that out for the sake of a video. This ends up being 1/2 ln 1 plus y squared. I don't need absolute value because that will always be positive inside there. Do the u sub. U is just 1 plus y squared. Du is 2y. Go through that whole process for that. I want you to verify, but we won't do it here. So now I have f of xy. So that's 1/2 x squared plus x times tan -1y plus 1/2 ln 1 plus y squared. They just wanted us to set it up. That's all they wanted on that one. I can't even go further because I would need bounds. So that's what that little f is. Don't let the calculus in there trip you up. Look things up using tables. I probably will put a table on your final. I will do so. I'll have to make a note to myself. Okay. We're going to we have 2 more problems, but we are going to make them in x, y, z, 3 variables rather than 2. All right, so find the work on that force field with x, y, and z from point A to point B in 3 space. It's done the exact same way, except for to show that it's conservative, we have to find the curl. Now remember, the curl is just a cross product, I, j, and k. Then we put this like partials here, and they're just operators, partial of x, partial of y, and partial of z. They're nothing alone, but they're operators. And then we put the components here, y, z squared, x, z squared, and 2x, y, z. And when you work this out, this is what I do. I just cover them up. So cover this up. And then whatever they touch, that's what I do. So partial derivative of 2x, y, z with respect to y is going to be 2xz. Minus the partial of that with z is 2xz, which is 0, and that's what we want, right? We want the curl to be 0. At any point, if you get right here and that's not 0, you can stop. It's not conservative, which means you would use methods back in the first 15.2. Right now, I covered those up. Delete these x's. Right, partial of x with 2xyz. That's going to be 2yz. And then the partial of z to yz squared is 2yz. That's a 0. That's what we wanted. Plus, okay, now I do this last column. There we go. dx, d dx of xz squared is going to be, what is that? Z squared. And then the partial of y with yz squared is z squared. So we're good. So this thing is the 0 vector, which tells me that f is conservative. That means I can use the method that we've been using. All right, so the integral, first we want to find x, y, z. It's going to take multiple steps here. We take the integral of the partial of p with respect to x dx. All right, that is yz squared dx. We get x, y, z squared plus h of y and z. And I'll show you how to deal with that y and z after this problem. But here's a trick if you want to check here is you could always just write down this problem, x, y, z squared, and ask yourself, is there going to be anything else added to get, because I know that's the f that gives me the gradient of that, right? The gradient will be that. So if I take with respect to x, I get yz squared. If I take with respect to y, I get xz squared. If I take with respect to z, I get 2xyz. I don't need anything, so it's just a plus c. They all work out. If that happens, you can just eyeball it and see that. If not, example 6, I'll work through the method on how to get to that. All right, I have f there. So now, to find work, I take the integral over c f dr. That's just the gradient of f dr over c. All right, so I plug in. The points for this was 1, 3, 2. Minus f of 0, 0, 1. And we get 12 minus 0 once you plug those in. So you get nice, pretty 12. This one's great. If you can eyeball it from here to here to determine that this is just a 0, then great. Or just a constant c, fantastic. If not, you'll have to work it a bit of a different way. So I'm going to do our last problem. I'll work it that way that I'm talking about. All right, so first we do have to show the curl is 0. It's good practice for the curl. So I, j, k, and then I put my operators. And then each function. So cosine y, this one's going to be z squared minus x sine y, and then that last one is 2yz. I'll do that so I'm not cramming it in there. All right, so I cover, and I get partial of y with 2yz is 2z, minus the partial of z for z squared minus x sine y is 2z, it's 0, so we're still good to keep going. If it wasn't 0, I would just stop. That should be a minus. Won't matter because it has to be 0. I think I put a plus up there. Yeah, so this should be a minus, but it won't matter because it should be 0. Right, I erase that one. I cover up the middle column now. d dx of 2yz, that's going to be 0. d dz of cosine y is 0, so that's great. That's easy. And then the last one, cover that column up. All right, and we get partial of x. With that whole thing, we get negative sine y minus, okay, d dy of cosine, that's negative sine y. Those are going to get us a nice, pretty 0. So we have the 0 vector, which tells me that f is conservative, which tells us that little there is a gradient of a little f that gets us big F. So we know we can look for one. If it wasn't conservative, remember, we just go back to 15.2 methods. There's also a method that we'll have in a certain, in a special case, and that'll be 15.4. All right, so now to find f of x, y, z, I just work backwards. It's going to be the integral of the partial of p with respect to x dx. So that is the integral of cosine y dy, dx, sorry. All right, that gets me x cosine y plus h y z. It has both of them. It could be y's and z's, because if I take the derivative with the x, the y's and z's could go away. So what I do from here, is I have f. It's the same as the other ones. I take the partial with respect to y, and I get negative x sine y. And then we got to talk about the derivative of this. This is actually the derivative of h with respect to y, not h prime, because there's a y and a z. I can't do that. Now I set this equal to my partial of f, which is p, q, r. It's q. So we get z squared minus x is sine y. So we get the partial of h with respect to y. Those go away and I get z squared. Right? This tells me then that h of yz is equal to 1/3, and it's with respect to y actually, so it's y z squared plus some other function, we'll call it g of z. So I know f is equal to x cos y cosine of y plus y z squared plus g of z. I'm not done because of that g of z. Okay, I could take that f now. Instead of doing the partial of y like we did, we could do the partial of z and set that one equal. Okay, the first term's gone, then we get a 2yz plus g prime of z. And now I set this equal to r up there, because I know that is the partial of this f with respect to z. That's 2yz. That tells me that g prime of z is equal to 0, which tells me g of z is just c. So I have my f now. F of x, y, z is equal to x cosine y plus y z squared plus c. All right, now we have that, so I can find the work over c, f dr. I can change that big F to the gradient of f since it's conservative, and then I can use the fundamental theorem of calculus. So that's f of 2 pi 1. That's the points at the top. F of 1, 0, 0. Right? This ends up being 2 cosine 2 pi plus 2 pi minus 1. That's plugging those in, which leaves us to 2 pi plus 1. So that's how much work it would take to move on that path from A to B, those 2 points in 3 space, just a straight path through this vector field. This vector field could be forces like wind or water, stuff like that. Pretty neat stuff. Those of you that are going into meteorology, these are big with radar maps. I see this in practice in a storm chaser car. So I definitely know that this is in practice. Watch Weather Channel radars, and you can start seeing these gradients, and you can start seeing stuff like that. So this is 15.3, moving a particle on a path through a conservative vector field.